let's again call on the fact that an integral of a matrix quantity can be done term by term, and we'll bring the integration into the matrix symbol. And here we have, for instance, the integration inside on that term and on that term. So you have to be able to integrate linear terms and quadratic terms in x, leading to these expressions. Without worrying you about the details, this will integrate out to give these values of L over 6 and L over 3. But it's more convenient to rearrange the answer by factoring out terms such that you have the total load appearing on the left here, and then showing that 1/3 of it acts at the left node and 2/3 at the right node, and I've sketched that over here. Now some of you might say, well, I could have guessed that because my intuition would tell me that in some sense 2/3 of the load should go to the right. And what you may be dealing with is memories of handling beam problems with lateral loadings. And actually that intuition is not relevant to this problem. This is a statically indeterminate problem, and either node could have carried the entire live load and kept the body in equilibrium. It's only an energy idea that for the linear shape functions, you can redistribute the loads in this way and then get the same energy through those shape functions as the original triangular loading would have done. Let me review, though, what your intuition from the beam problem is, just to expand on this a little bit. That if you had lateral loading on a beam and it went to the side like this, and you actually showed as such, you know that the center of pressure on the beam would be at the basically the center of area of that loading pattern. And then because of moment equilibrium, you would say that 2/3 of the reaction force would be at the right and 1/3 at the left. And that's a good concept, and it's a linear concept. It happens to agree with the current example by accident, though. We don't have moment equilibrium that requires that kind of a predetermined balance of forces. But rather, in our case, it's just the energy equivalence. Now, you get the same answer because the shape functions are linear, and the moment balance that you were doing in your mind in the beam problem was also a linear process with distance. So the two answers came out the same. But if you want to push your luck a little further and you think, well, I can see the answer, then consider a 3-noded truss, and you would find then that it's quite difficult to decide how to redistribute a load. Even a constant load is very difficult to decide how to redistribute. And so the equivalent nodal load concept is very powerful and based on this work equivalence, which is not intuitive for the average complicated situation. Now it's time for a problem session. Some of you might wonder about these problem sessions. Where do these problems come from? Some of them were developed to prove a point in class as an example, and many of them were developed for exams. So you'll find many of these questions, such as the first one that we're going to do, were originally meant to be exam questions and requiring about 15 minutes of a student's time. The first problem is a constant strain triangle, and just to make people think about the interpolation process, I'm saying that the triangle moves through a distance at the lower left node of 1 unit in the direction to the right. And that would lead to a final shape of the element, which would have straight sides of this bunched up triangle shown here. And the problem is to find the strain in the inside of the element. This really is a matter of interpolation, so we have to get serious about how the shape function will propagate that disturbance at the node into the interior of the element. So our shape function for this particular problem for the first node would be taken to be a constant times the equation for the line or the surface that would pass through these two nodes over here. So really, as you know, the equation of this line would be a function, could be written originally as y equals f of x. But with some work, you can find out that this is the formulation. In fact, y equals the y-intercept, which is b, and then minus the slope, which is going to be b over a times x. And then if we non-dimensionalize this, let's see, we can divide through by b, and then you'll get this equation. Alright, how do we evaluate that constant? We do it by setting the displacement at the node number 1 to be unity, and evaluate the x and y at the origin, which is 0. So you get just that the constant times 1 has to equal 1, or in other words, the constant itself is 1. So we know what our shape function is. It's merely this quantity here. The non-dimensionalization that I did actually forced it into the proper form. And what we really need is the strain law B, which is the strain displacement law times the shape function. I'm going to use summation form to help in this problem because I can identify that there are a lot of zeros involved, and it will help organize the problem and focus our attention on the variables that we do want. So in summation form, the general ith component of strain has to be related to the strain displacement law times the shape function times the nodal vector. And notice that in each case in that multiplication you're summing over a common index, so that J would be the index representing the column of the D matrix but the row of the N matrix, and K likewise plays that role in this multiplication. We really are only interested in one strain. We've been asked to provide epsilon x, which would carry the index 1, and so we only want I equals 1, which will limit there, and I've shown that on the left side here. But that also implies that we only want I to be 1 in the D matrix. Then we only are given a displacement in the U1 component and not the other 5 components. So we're only interested in U1 for the displacement over here. Now that's the K index. So, and furthermore, the specific value is unity, so I can go ahead and put that in. But that drives this K index to take only the value of unity. That means we've effectively summed out the K index, and the only one that's of interest remains. So K really was only summed over 1, and the summation here then turned out to be degenerate. If you write out the D and the N matrices, they appear as shown here, and I'm anticipating what's going to happen in this multiplication, that I only need the first row of the D matrix, namely this row. I only need the first column of the N matrix, which is this column. And then the summation proceeds on, there are only 2 terms involved, from the J index to be 1 and 2. Now what that means is you take across this direction, multiply down this direction. And note again, you're going to get a partial on x of this polynomial, and then 0 times 0 over here. So it reduces only to 1 term. I'll write down the surviving terms in our strain expression. Here we see that we have the role of the geometric strain displacement law and the geometric shape function. The derivative kills off the terms except for the one coming from the x over a, and you get a constant strain over the face of the element in the x direction with a negative value, so it's a compression. That makes sense because what you've done now is taken an original triangle such as this, you've moved a node that has made the left end shorten the horizontal lines that are extended across here. It's not quite intuitive that you would get constant straining from bottom to top. You might have thought that this would compress the bottom proportionally more than the elements at the top. But you see, this is a straight-sided element, and that compresses all of them uniformly. If you followed this problem through, you would find that there's no strain, epsilon y, throughout the body, but that there is a shear strain, as you can imagine here, because you're distorting angles. But I think the person who's done a lot of stress analysis would be a little uneasy about the fact that this displacement in the horizontal direction causes no strain in the vertical direction, no epsilon y, because you're used to the coupling through the material law that would give a Poisson ratio effect, that you might get forces up there in the transverse direction to the direction of load. That's partly correct, that force-like things can be coupled, but this is purely a geometric argument we've gone through. And so at the level of nodal displacements and interpolating the displacement field and the strain field inside the body, you don't get any material coupling at all. Problem 2 will be an exercise on equivalent nodal loads. I've picked 2 of the hardest cases I can think of that will test your ingenuity, and one is a distributed load over part of the body, and the second is a concentrated force in the interior between the nodes. So it's really not clear intuitively how to redistribute such a load pattern, and would be difficult by older-fashioned lumped load ideas. But we will be able to make consistent loading here that will cause the same work as the original distributed load would have. The dimensions on the loading are force per length on the left problem, and on the right the dimensions are force. Now, we haven't yet spoken about the Dirac Delta function, which is useful to handle these concentrated forces, so I'll have to say just a little about it. The Dirac Delta is a hypothetical function that takes an infinite value over some special point. Let's call that point x0. But yet the delta function is integrable, and in fact the area under the curve turns out to be unity. A further refinement is that the delta function is not considered just one such function, but rather the limit, as this figure gets sharper and sharper and narrower until at the limit you have just an extremely tall spike at the point of question x0. So it's possible then to take such a function, the delta function, and multiply it times some distributed function such as f of x, putting it in here, and then you will find that it will evaluate that function at, indeed, rather than a unit value, at f at x0. Some of you may not be comfortable with this if you haven't seen it in a physics problem. And I do say more about this in the chapter on classical plate theory, where concentrated forces are really important. So you can look ahead to that if need be. We'll start with the solution for the distributed load shown in the left figure on the previous slide. And what most engineers forget at some point in their career is that you can have functions that are 0 over a part of a region and then non-zero over the other part, and when you're asked to integrate that function, then all you have to do is bring the limits up to knock out the parts where the function is 0. Often that's easier than drawing some kind of a strange function in here that does in fact have 0 values over a region you're interested in. So you take the full value of the distributed load and you account for the fact that it's 0 outside of that region of interest by not integrating it over that region outside of your interest. So our limits on the integral are L over 2 to L. And under that philosophy, then, it's pretty easy to carry out the integration. You take this constant term, which will factor out front. You do integration term by term in this vector and evaluate at the limit points, and you'll get this expression here. In the ratio of distribution, that 1 part of the load goes to the left and 3 parts go to the right. So this load here, as originally conceived, is redistributed to the nodes as shown below in the ratio of 3 parts to 1 part. And I guess, again, we could do that intuitive discussion about whether that appears to satisfy somewhat of a balance with regard to the center of pressure here, and it again does, because we have linear shape functions in this problem. But again, that's just a fortuitous coincidence and doesn't reflect any real physics. But nevertheless, these are intuitive in this case. Now let's do the second equivalent nodal load problem that had the concentrated force. And this time we will in fact integrate over the total region of the problem, and we'll make the function itself bear the burden of going to 0 in the non-interesting regions. So we use the Dirac Delta function here, and times the constant, and times this shape function. Selectively, that integral, in fact, then will evaluate the function at the point, in this case, which is 2/3 of the way across the truss element. And so delta of this quantity will, in fact, make us evaluate x at 2/3 L. And when that's done, you end up with this distribution below, where the load now is being redistributed in the form 2/3 at the right side, 1/3 at the left side. And I think that again is intuitive, because since this was 2/3 of the way to the right end, that seems like a logical way to do it. But again, is being done on the basis of an energy balance and not some sort of force balance. Problem 3 concerns the hypothetical element that might be formed from some given data. Here I'm proposing that you have a mapping matrix H inverse as given, a displacement function matrix shown here, a strain displacement law, and a material law. Now this is meant to be really hypothetical, but as we go along we might have some clue as to what sort of an element this was. The strain displacement law is interesting because it shows that you only get strains in the x direction, and yet the phi matrix shows that you have a body that has both y and x coordinates. So it seems to be a body lying in 2 dimensions that has probably 3 degrees of freedom, which is a little strange, and has a material law which is similar to an elastic body, where stress will be proportional to strain. So what kind of an element is this? We'll assume that the initial volume of the element is V0, that is the undeformed volume, and the question is to find the stiffness matrix, and then to comment on that when we get done as to whether or not there might be a rigid body mode present. And that means, would there be one of the degrees of freedom perhaps that is degenerate and doesn't contribute any stiffness? Well, this problem has been posed in a mysterious way, and so it's going to be fair for us to use any kind of treachery that we can to solve it. First of all, it appears there are 3 degrees of freedom because the H matrix is a 3 by 3 matrix. we see that the x and y are involved. We suspect there would be a scalar field with 3 nodes rather than a vector field with, say, 2 nodes and 1 degree of freedom at one node and 2 at the other. So that would be a somewhat of an odd element, although we already have our suspicions about this one. It appears that there's a rigid body mode already from looking at the phi matrix that has a constant term. That means one of the generalized coordinates will allow the field variable to take a constantly elevated value over the body. It's not completely obvious yet what all that implies, but we'll come back to that and we can show that more definitely later on. The shape function matrix is the first thing we need now if we want to start to develop our stiffness matrix, which will be going in this logic from here on. That we multiply the phi matrix times H inverse. That's an easy forward multiplication done here, and yields this shape function matrix. So it's fully populated with x and y terms. Next, we'd like to calculate the strain matrix, and that's just the strain displacement law times the shape function matrix. Well, that derivative kills off one of the terms and gives us constant values on the others. So this is a constant strain, although we don't know quite what we mean by strain in this problem at this time. And also adds further suspicion that we will have a rigid body mode, because one of the motions of this body has led to something that causes no strain. Then the stiffness matrix can be written out in the general form with the B matrix. We can substitute our specific B matrix in as in this case, a column vector, and then in this case as a row vector. And with our Q material properties, we do the multiplication of the latter 2 matrices first to get this intermediate result. And then we're at that position again where we're taking a 3 by 1 matrix times a 1 by 3 matrix, and this will expand and give us a 3 by 3 matrix shown in the next figure. So we expand the integrand and get the 3 by 3 matrix there, and then that can be integrated term by term to yield the final stiffness matrix. In this form, you can see that the first coordinate would be an unusual one in that it doesn't have any stiffness and it doesn't couple with the other coordinates in any elastic way, so it's elastically uncoupled, and that's further illustration that there is something like a rigid body motion in this structure. It would be hard to imagine how one coordinate could be so thoroughly uncoupled. It's almost as if it's a grid point singularity in this case. We talk about things like that later. And by the way, rigid body effects like that are common in other physical systems, such as in electrical circuits, where you can get a DC voltage shift in an AC circuit. And of course, good practice is to ground that DC voltage so that you don't get the voltage drifting around. And the same thing could happen in a temperature field. Now, that's the end of our problem solution, but I do give a little hint as to how I laid the problem out with the secret geometry that I used in working out some of the geometric ideas. So behind this mysterious element was indeed a geometry as shown below. The fourth problem will be a study of an isosceles plane stress triangle, and we will work out the ideas of shape functions and equivalent nodal loads. It's actually a pretty long problem. It's almost like a case study. Here's the triangle. It has an interior node number 4, and the questions that I'm going to ask have to do with, are the shape functions linear or not, and why? find the simplest set of shape functions. What are the equivalent nodal loads at node 3, say, for a constant body force in the x direction, which would be a surface force in this case? And then finally, is this a conforming element with neighboring elements? Can you say anything about that? The solution to part A in our problem has to do with counting the number of degrees of freedom and then the number of terms in a polynomial to see if it can be done with just a complete linear polynomial. The argument really comes more from the displacement function phi approach rather than the shape function. And what happens is you find that there are 4 degrees of freedom in the problem, representing a displacement, say, in the x direction at the 4 nodes. Yet a linear polynomial in 2 dimensions only has 3 coefficients, so there's no way that you can create a displacement polynomial to effectively control 4 nodes with only 3 coefficients. So you're going to need at least one quadratic form. And that might be an xy term or an x squared or a y squared. At this point, you don't know until you look at the polynomials for the specific shape functions. You'd prefer it to be geometrically isotropic, of course, and involve xy in preference to the others, but you could get both x squared and y squared. There's no guarantee when you go to shape functions that you are as well controlled as you are with the displacement polynomial formulation. Nevertheless, we go ahead with our shape function ideas in part B, and I'm going to use the product idea that the shape function representing node 1, to take a unit value here, will be the product of a surface that passes through these vertical lines that knock out the displacement at nodes 2, 3, and 4. And the product of those lines is this x times x minus a with an arbitrary adjustable coefficient c. If you evaluate that to be unity at the left end at the node number 1, you put in the values for x here and here, and you come up with an expression that evaluates c as 1 over 2a squared, and that appears as a normalizing factor in the first shape function. The shape function for node 2 on the far side is identical in logic, and you only come up with x plus a there instead of x minus a. So there's a kind of a symmetry of that shape function. The third shape function is obtained by similar arguments. Here we want a unit value at the upper vertex, and we'll take a product form with the equation for the 2 green lines shown below, and causing this product with the coefficient c to be determined. And again, that's evaluated at the vertex with unit value, and you put in the b values where, in this case, y is taken to be b. You get a normalizing factor and apply that for this shape function. Now we're left only with the shape function for the central node, and that's found by the product rule by the horizontal green lines. And again, we have these 2 functions, adjust the coefficient, and get this fourth one. Now, the process we're doing is not unique. You can get different polynomial forms if you're willing to have more fancy surfaces, but these shape functions that you have just seen develop don't involve more than quadratic forms. They actually do have y squared terms. They have x squared terms. Looking back at them, I don't see any xy term in it. So they've turned out to have a particular form, but it is a quadratic set of polynomials. And we can put those into a shape function matrix below here so that we know everything about the problem in the geometric sense. Part C of our problem has to do with calculating equivalent nodal loads at the top vertex due to a uniform horizontal traction across the face of the triangle. So the sketch shows here what we are interested in, this horizontal force, call it a Tx, and then the required force replacements F5 and F6. So that's going to involve an integration over the area of the body of this surface traction, and the shape functions that we just developed are the major ingredient here. I'm going to go into the summation convention here to help eliminate some of these terms rather than write them all out. Now, if I is the free index indicating which of the force components we're getting, then that appears in the shape function here and in a free index way, so it's not summed over. But the J index, which is the component of traction, is being summed over, and takes the values 1 and 2. Now the only thing is that the T2 component here, which is the Y component, is actually 0. So we don't need to do that sum on the J here, but rather just set it to be unity. And so that knocks out the summation in effect, and we'll only need N1I and T1 as a result. So our form has reduced to this form below here. Then we can substitute in the values for the free index of the horizontal component F5 related to N15 and the Tx, or the T1 component, and then F6 is the vertical component times N16 times Tx again. Now this is going to vanish in a second because this component is 0, but I'm just previewing the results a little there. I'll write down the shape function and include only the relevant terms. Here we have the component N15, and here's the component N16, which is 0. We're interested in the horizontal component and the vertical component at this upper node. So starting with the horizontal component, we put in for the free index the 5, and in here we have the shape function term N15, and then this is constant. That can be integrated over the face of the element, and by the way, that integration isn't trivial, because with those slanted sides you need to do a careful adjustment of the upper and lower limits on these integrals. I found that fools many people in the field, and many of our graduate students forget about integrating over a non-rectangular domain. Everybody can do a rectangle, but to do a triangle is tougher. But in any event, you evaluate that integral and you come up with this force acting at the upper node in the right direction. And through some work I've done subsequent to this, I've found that that's actually 1/12 of the total force in the horizontal direction. And so it's really a fairly small fraction of the total force that triangle is exposed to. Meanwhile, the vertical component, F6, would use the shape function N16, which would have occurred in this location, replacing this shape function, and then we would have F6 on the left side, and that vanishes. So the horizontal force doesn't cause any equivalent nodal load in the vertical direction. And when completing the whole set of equivalent nodal loads, I was astounded to find that 9/12 of it acts at the center of the element, and only 1/12 out at the nodes at the periphery. So this is one of those non-intuitive situations where a higher order element, namely a quadratic field inside, distributes the forces in a way that is not intuitive, and in no way could people have just guessed this answer. Part D of our problem had to do with whether the element would be conforming or not. And the answer to that involves kind of an end run, we say in football notation in the United States, that you have to think about what would control the deflections on the edge of an element. And you'd like that control to be common between element A and B that adjoin that edge, so that both elements use the same information to calculate whether that edge is a straight line or bows to the right or bows to the left. Unfortunately, in our element, if we take the, say, this upper left side, a cut along that side you would find, if you look at the shape functions, will be parabolic. It will have quadratic terms, and in general then could take a fancy shape. But unfortunately, you only have two pieces of information from the nodes that lie on that line, and therefore, in order to uniquely prescribe what goes on that cut edge, you must use information either from the mid-size